Yeah, okay. Hello, everyone. Welcome. So today we will have the second part of Gianluca's talk. Yeah, over to you, Luca.
Yeah, thanks. So thanks again for being here with me for this second lecture. Okay, the plan today is to go through the details. So we go through flat structure today. We go through flat structures, and time permitting, this is quite unusual, but time permitting, I give you some other motivation because that part is less important. So it's something that if I have time, I can mention that some connections with second order differential equations. Otherwise, it's not necessary. But I just keep that part for as the last thing according to the time. Okay. So first thing, some recalling. So these are kind of warm up. So flat structures. I recall these flat structures are geometries locally modeled on E2 or perhaps R2 if we do not preserve any metric. And then we can, when we have flat structures, we can think translations. And then there is an associate group equal to C. We might have some isometries. Then S1 semi-direct C. And affine, complex affine. And this is C star semi-direct C. So flat structures in this sense with this notion, sorry, this notation. So is this couple E2 and this group G, where G is one of these groups. Okay, and so we call them accordingly translation structures or translation surfaces, Euclidean structures. This is Euclidean. Or complex affine structures. Well, then geometry structures. On surfaces, SG&N. So G is genus, and N is number of functors. Well, what is a geometry structures on a surface? This recall is a maximal atlas. Of possibly branch charts and transition functions in G, where G is one. Once again, it's, in our case, so for we say, okay, let me say it this way. In G, so flat is that G could be C, C S1 semi-direct C or C star semi-direct C. Well, and I recall you that whenever you have these atlas of charts, then so this when you have a geometric structure in general, you can define two objects, namely a developing map from the universal cover of my surface into the model space X, and this is equivalent to respect to group homomorphism from pi1 SGN into my group G. And this object is called holonomy representation. Or let me just mention monodromy sometimes. If we think about to some ordinary differential equation associated to the structure. But this is just we need this notion if I talk about some further motivation. Time permitting. Well, I recall you then the main question was, suppose we are given representation. So you have this homomorphism down, this is just an algebraic object, not associated to any geometric structure, but we may ask G is one of the above groups. Then does it rise as the holonomy of some flat structure on SGN? This is the question we would like to answer. So first, let's start with translation surfaces. Translation. Okay, so here we have E2, C. And so we have this atlas phi alpha from U alpha into C. Transition functions are just translations, where C is just some complex number. But there is a quite standard fact that you flat structure, translation surfaces. So this notion of translation surface with maximal atlas taking values on C and transition function to be translations is a geometric definition. So let's say this is a geometric definition, but we can also have some complex analytic point of view. And the point is the following: translation surface is equivalent to Riemann surface X and holomorphic Abelian differential. These are one form, but they are called Abelian differentials. Omega on X. So let's see briefly why we have this kind of equivalence. So in one direction, we suppose we have these atlas of charts. So we are given these atlas. And then since transition functions are holomorphic, the atlas define on underlying conformal structure. So some Riemann surface conformal structure X. And now we use the charts for defining the Wieden one form, the Wieden differential, in the sense that we can define this family phi alpha pullback of TZ, where that is just the standard one form on C. And this family globalize to one for omega on X, because transition functions are translations. So what happens when you have two, you have this family of local one forms, but if two charts overlaps, you want that these two local one forms agree in some sense, and the agreement is given by the fact that translation functions are translations. So when you apply the differential, the translational part is completely cancelled out. So they agree, are translations. On the other direction is that, suppose we start with this couple, then pick P any point on X. Suppose here is my point P and here is my open some U. We define a new chart on U as follows. We find Z of some sort. Let's say my point Q. You can find Z of Q, nothing but as the integral from P to Q of omega. And okay, sorry. And this is well defined. Is well defined as it does not depends on the path zoning PAQ. What do I mean? I mean that we can integrate omega along this path. So the red path can integrate along the green one. But since this area here is simply connected, they are homotopy, and that the integral agree. So integrating along, say, this gamma 1 or this gamma 2, they give you exactly the same value. So we can define a collection of charts, and now we have to check that if you pick two charts like this, transition functions is a translation. So now suppose you have two charts like this. So here is some point P, here is some point R, and I pick Q somewhere here. Suppose we have already defined the coordinate Z on this open set, and here we have defined W. Then we can consider the coordinate Z of Q, because Q lies in the intersection of this, say, U and V. And this, by definition, integral from P to Q of omega. On the other hand, W of Q is the integral from R to Q of omega. But what is this guy? This guy is just integral from R to P of omega plus integral from P to Q of omega. And this is my coordinate, ZQ, and this is a constant. So we have said that WQ is nothing but ZQ plus C. And this gives the equivalence between these two definitions. So from now on, translation
Excuse me. So here integral R to B might not be well defined, right? From
Sorry?
R to P. The integral from R to P might depend on the path, right? Because they are on two different charts.
Yeah.
So it might depend on the path, right?
Okay, so you have to assume that, okay, you can assume that the union of U and W is simply connected up to shrinks this set. You have through shrinks open set, you assume that the union is simply connected.
Okay.
And then if you choose another path joining them,
right.
Even these are simply connected. So the two values agrees. Of course, if you pick this U and B, W, U and B very, very big, then they're no longer simply connected. Then yes, it might depends on the paths choosing P and R. But you can also think to fix one path joining them, and then you can relate coordinates Z and W. Okay. Of course, if you choose different paths, means that they are not homotopic, means they are not simply connected. But this is something anyway that you can get rid of as soon as you shrink these open sets so that the union is also simply connected. Yeah.
Okay.
Okay, so from now on, translation surface is mostly seen as just this kind of couple, X omega. Well, okay, now we can introduce one notion of volume of X omega. And the first definition, we can say there is a geometric definition, say geometric volume. In this geometric volume, say Paul X omega is just defined as an integral over the Riemann surface of omega wedge omega conjugate, and this is supposed to be greater than 0. It can't be negative because let me give you an example. Like it's one of my favorite example. Perhaps you have seen this other times. Suppose we have this L shape, and okay, let me use that. Is it no? The orange dot is not visible. Okay, this is not a good color. Let me use maybe purple is not what I want. Dot. Oh, sorry. Okay, so I can identify this guy with this guy, and I can identify this guy with this guy, this guy with this guy, and finally I can identify these two. So this is a kind of octagon. This is not the usual octagon, because there are two sides, two couple of sides are aligned, but it's an octagon. And I can identify the opposite side by using translations in this way. You can see. And so when you identify the sides, what happens? You get a surface of genus 2. You can convince yourself that you get a closed surface of genus 2. All the vertices are identified. You get one point here, and the angle around this point is 6 pi. Why? Suppose we start from this point here, where it's the arrow. Then there is 1 pi by 2, another pi by 2, pi by 2. Then I'm here pi, 3 pi by 2, and here pi once again, pi by 2, and then I go back, I return to the initial point. If you sum these inner angles, you get exactly 6 pi. So this is a branch point. Is the unique branch point for this structure. Branch point, I remind you, that means all charts around it are branch charts. And what is the volume? So we have used translation, so we have used the first definition, but there is an underlying Riemann surface, and there is a one abelian differential omega, and the volume of this guy is just equal to area of this L shape. So the area, the volume is just given by the area of this guy. We talk about notion of volume because this notion, first of all, the volume can be generalized to higher dimensions. So, and the terminology used even for areas is volume. So we use that. But you can think exactly as the area of this L shape on R2. And so this has to be positive. This is a necessary condition. So now, what we can do, so pick a symplectic basis alpha 1, beta 1, alpha g, beta g of H1 SGZ. This is the first homology group. And we call it this the abelianization of pi 1 SG. And this is a theorem, something that it's something classical. That the volume that I told you is can be seen as the integral over as omega was omega bar. This is equal to by Riemann bilinear relations is equal to I by 2 sum of integral over alpha I omega alpha beta I of omega bar minus integral omega bar alpha I integral of beta I. Okay, now keep this there for a while. Now you know that whenever you have a translation structure, translation surface, then there is an holonomy representation. So it's say x omega is an holonomy representation. But since the image, since the target is an abelian group, this boils down to a representation from P1 SGZ into C that we can call chi just because I don't want to use the same letters. And there is this fact that how is the representation defined? Every gamma is sent to the integral of gamma, the integral of omega along gamma. This is a standard fact that you can prove. And so if you use this fact, this implies that volume of x omega is from this equality star. This becomes 1 I by 2 sum of chi alpha I chi beta I bar minus chi alpha I bar chi beta I, and this is nothing but summation of the imaginary part of this product. Well, so we have found one condition that we want the volume of x omega to be equal, say, let me say this thing. This is also called vol of chi, and this is algebraic volume. This is called algebraic volume. So the first condition is that the geometric volume has to be equal to the algebraic volume, and this is and I mean I don't write it again. So and this has to be equal to this guy here. Well, now suppose there is one special case. Suppose that we have the image of this guy into C is a lattice lambda. And so this means that C mod lambda is a torus T. Then it happens that chi is nothing but mapping from SG(Z) into the first homology group of the torus with integer coefficients. And this implies that there is a mapping F from SG to T, which is homotopic to the developing map of this translation surface. And by some theorem of Edmonds, the degree of this mapping has to be at least 2. Otherwise, otherwise, if the degree would be equal to 1, then this mapping would be homotopic to a pinching, and then we get a contradiction, topological contradiction. So we have this necessary condition that the degree of this mapping has to be equal to, but this then implies one condition on the volume. Volume of chi, so the algebraic volume, or volume of x omega, so geometric volume, has to be at least 2 times the area of C mod lambda. And then we have found this second condition. If the image of chi is a lattice, then we want that volume of chi is 2 times area of C mod lambda. Well, these are necessary conditions. And some old theorems, this theorem by Out, that I already stated this theorem in the previous lecture, this theorem by 1920. And I should say recently rediscovered by Kapovich by using Ratner theory. So completely different method. So this theorem says that the necessary condition are also sufficient. So representation chi is the holonomy. So this means that this representation chi from P1 as G into Z, or if you want, rho, is holonomy if and only if the 2 conditions above are satisfied. Well, in this sense, so let me give you now. We talk about some other examples. So suppose we have this torus, and let's fix some symplectic basis. These are ordered symplectic basis. So we have alpha beta is a positive basis. This means that here we have this notion. If you look at the angle, we are going counterclockwise. Well, this is my topological surface. Now, one case can think the unite square 0, 1, I, and suppose that chi alpha is equal to 1 and chi beta is equal to I, then the volume of chi is equal to 1. And if I look at the interior, I can, maybe I can also use this red, and let me use another color here, say blue. If I identify these opposite sides by using the red arrow and the blue arrow, I got exactly this torus. This is alpha and this is beta. So I get the torus with some complex structure and a symplectic basis oriented as alpha beta. But now look at what happens if we consider this, not this square, but the mirror reflected square. So this chi alpha and this chi beta. So here I have minus I, and here I have 1. If I look at once again the interior, if I look at the interior here, when you have this square, you can still glue the opposite sides by using translation, because you can do this, but you can convince yourself that the final torus is there is one angle generator alpha is consistent with that the first one, but now the blue one runs on the other way around. So this is negative oriented. Here, the symplectic basis is negatively oriented. And indeed, if you compute the volume of this, let's call chi prime, this is exactly minus 1, so it's negative. So the point of the negative volume is that you can still view opposite sides whenever you have a negative volume, but you don't get a structure, and you get a complex structure, but this complex structure is not the usual complex structure, but is on C there are two complex structures, and so one is the standard one, so that 1 and I is a positive basis, and the other is when 1 and minus 1 is a positive basis. And so it depends on which complex structure you're choosing, the volume is positive or negative. And so this volume basically reflects this fact that on C there are two complex structures. Okay, so this is what happens for closed surfaces. And what about open surfaces? Okay, let's see once again this square. Look at this square once again. So before we have taken the interior, what happens now if we consider the exterior? Okay. Now the angle here, I'm running counterclockwise. So in this case, the basis, if I glue the opposite side, but I forget the interior, I just look at the exterior, what I get is no longer a torus, what is a one puncture torus topologically, is something metrically, it looks like something like this. And again, now I have two angle generators. And now this basis is consistent. What happens now, if you look at the corners, these are, each one is it's an angle of 3 pi by 2. So somewhere here, there is one branch point of angle 6 pi. And the infinity is a, say, pole. What do I mean with pole? I mean that in this case, the translation structure is defined by a Riemann surface X and a meromorphic differential omega. And so now omega may have poles. And this, and let me remind you this thing that, so recall that when you have some meromorphic form, then the number of zeros minus the number of poles, both counted with multiplicity, has to be equal to 2g minus 2. In this case, what happens? We have this zero, this is 0 of order 2. It is indeed a pole of order 2 if you consider the infinity for, because the infinity for dz, for the one standard form C, the infinity is just a pole of order 2. Well, so what happens here? So some remark: the algebraic volume is negative, but the geometric volume is positive. And this is what matters. I mean, there is a flat structure if the geometric volume is positive. For closed surfaces, that it turns out that also the algebraic volume has to be positive. But when you allow puncture surfaces, this is no longer true. And indeed, there's this theorem, quite a recent theorem by Shabarish, Chanakot, myself, and Shubhojoy Gupta, that any representation chi from P1 SG&Z into C, n is at least 1, otherwise we get contradiction, is the holonomy of some translation surface such that the punctures, say x omega, punctures are poles for omega. Okay, well, now let me talk. I'm going to conclude talking about fine and Euclidean structure. So we can also, even in this case, talk about volume. So we can extend the notion of volume, the geometric one, I mean, geometric volume, to Euclidean structure. So even for Euclidean structure, even if transition functions are not translation, but they are still isometries, so the structure may carry some singular Euclidean metric, then we can talk about the volume. And in this case, so you are given this some representation into a fine C. Then you can show the direct system mapping from SG tilde to C rho equivariant. This is a fact. This is something one can show. And volume of rho is just defined as the integral over SG of S fullback. DZ was the Z bar. This is nothing but, I mean, this is just the generalization of volume that I previously defined. Let me give you another couple of examples. So here we may think this is the regular octagon. No, this color is not good. And here, if you identify these sides, then you are no. Okay, well, so I glue sides by using rotations. So we get on a Euclidean structure, because structure on the surface of genus 2, you can, I mean, this standard with the octagon gives you a surface of genus 2, but you can also have something more weird, something like this, and then you can glue opposite sides. These are affine structures, complex affine structure. You basically glue the opposite sides by using a complex affine transformation. You can always find, when you have 2 points, another couple of points, you can always find a affine transformation sending the first couple to the second one. And here, since the affine transformation affine maps do not preserve the standard Euclidean metric, here we don't have any metric, and then also the notion of volume here doesn't make sense. So here, the notion of volume does not make sense. Okay, so same kind of question. We would like to, we are given one representation from P1 as G into affine C. And when is this, when suppose we are given this representation, we would like to know when we have some structure associated to that. And there is this theorem by Ghazouani, I think it's 2017. And he says that if rho is Euclidean, then rho is holonomy if and only if volume of rho is positive. If rho is, say, strictly affine, it means not Euclidean. Then rho is holonomy of some branch affine structure. Branch means that we have some branch points. So there are branch points. Affine means that we are looking at some, I mean, an affine structure, then it's exactly what we this says, so we are on R2 model on affine C. Well, even in this case, you may wonder what happens for open surfaces. And so suppose we have this representation from SGN in affine C. Suppose n is at least 2 and rho is not trivial. Then something I proved recently with Shubhajay Gupta is that rho is holonomy of an affine structure on SGN without branch points. If we allowed n, if n is at least 3, then even the trivial representation is holonomy. And this comes from the fact that if the trivial representation is the holonomy, then you can get some branch covering over the sphere, CP1, branch at 3.01 and infinity. And this comes from some, Edmond, Kulkarni, and Stone. So if there is a branch covering from a surface of GSG to the sphere, there are at least 3 branch points that we assume to be 0, 1, and infinity. And so when n is 2 or 1, if you want to find a structure, if you suppose the existence of a structure with trivial holonomy, then you get some contradiction. So that's the reason why for the trivial representation, we need to assume n is at least 3. For n is equal to 1, there are some other exceptions. And for instance, representation from SG1 into Z2, which is a subgroup of affine C. This cannot arise as the holonomy of any structure, affine, any complex projective structure. And then, if you remember by hierarchies of geometries, no affine structure, because if you remember, complex projective structure is something weak than affine structure, affine structure. So it might happen that there is a representation in affine C, which is not the holonomy of some affine structure, but it could be the holonomy of some CP1 structure. But also on the other end, if you have a representation complex, so in affine C, and this cannot be the holonomy of any complex projective structure, then in particular you have not the holonomy of any affine structure. And this is exactly what we have proved. Well, so this is the scenario for affine structure. There is this scenario for affine structure, flat structures on open surfaces. And due to the lack of time, I don't go through the other motivation related to ordinary differential equations. But so I think I stop here. So thanks.
Yeah. Yeah, can you hear me?
Yeah, I can hear you.
Yeah. So any questions? Luca, you told some result. Can you go up a bit, scroll a bit up?
Yeah.
In 2016.
Yeah, here.
Yeah. What is the name?
Gazuani. I'll write you.
Okay.
Capital.
Okay.
Selim.
I see.
Yeah, he proved this kind of result.
Mm-hmm.
And
yeah, this is right.
Yeah, then there has been some other recent developments in the sense that he found branch structure. So, there are branch points, but in general, you don't know. I mean, using his proof, his methods, you cannot control these branch points in the sense that how many branch points are there or some these kind of questions. Instead, recently, another guy showed that you can prescribe the order of branch points, the number of order, and then up to some few exceptions, this prescription is not encoded by the representation. It means that the same representation could appear as the some branch affine structures with 1, 2, or more branch points of any order. So, he knows that there are some other geometric data that are not encoded by this representation. It's quite recent. Some 3-4 months ago, if he put this paper in the archive. Yeah, it's still a preprint, but it seems correct.
Yeah, so I don't think we have questions.
Okay.
So thanks a lot, Luca, for the nice talks. Yeah, thanks a lot.
Okay.
Let me stop the recording.
Yeah.